Okay, so this is the fifth lecture in the series on algebraic number theory. We're still working through Milne's book, the first section, Preliminaries from Commutative Algebra, and in this lecture I want to talk about local rings. So first, let me tell you what it means for a ring to be local. So we have a definition. A commutative ring R is local if it has a unique maximal ideal. Okay, so remember from your initial ring theory class that you can prove using Zorn's lemma, for example, that every ring has a maximal ideal. Every commutative ring has at least one maximal ideal, and it's local if there's exactly one maximal ideal. Okay. So I guess maybe just a small remark. This word local, you might ask, why is this called a local ring? And in short, I guess the short answer is it comes from algebraic geometry. But I'm not going to go too deep into that. Okay, so I want to make a remark here. Note that since every proper ideal so if I take any proper ideal, I can use Zorn's lemma to prove that it's contained in a maximal ideal. Okay. What this immediately implies is if A is a local ring, let's say with maximal ideal M, then if there should be a capital A, not a lowercase a. The group of units A cross is exactly the complement of M in A. So if I take an element little a here, then if I consider the ideal, it's not contained in any maximal ideal because it's not contained in the only maximal ideal. Therefore, it must generate the unit ideal, and the element must have been a unit. And similarly, since M is a maximal ideal, it certainly can't contain any units because it can't be the whole ring. Okay. So this is like a first basic fact about local rings. An important result that has to do with local rings is something called Nakayama's lemma. Okay. And there are like a million different ways to state this. I'm just going to state it one way and prove it that way. But if you've heard something else called Nakayama lemma, chances are it's equivalent to this in some way. So I'm going to let A be a local Noetherian ring. I'm going to let mathfrak A, so that A be a proper ideal. Okay, and we have the following thing for a finitely generated A module, say M. We let should have been A times M, so I'm going to define a subset of M It's going to be the set of all sums ai mi such that ai is in my ideal mathfrak A and mi is m. So it's essentially sums with coefficients in this ideal A. And Nakayama says two things. If there should be a condition here, should be a non-zero. If, oh wait, no, sorry. It doesn't need to be non-zero. I lied. Okay. If sums in M with coefficients in A equals M, the only way this can happen is if M equals 0, and B, if N is a submodule, such that M plus mathfrak AM equals M, then N has to actually be the whole module. Okay, so in a certain sense this says for non-zero modules over local Noetherian rings, if I take an ideal and I consider sums with coefficients in that ideal, this actually has to be a smaller module. I can't actually get the whole module in general. And part B is, these two things are like, if you know A, you can probably easily prove B and vice versa. So let's go ahead and work through the proof of this result. We'll start by proving A here. So we're going to suppose for the sake of contradiction that we have a non-zero module and an ideal A such that AM equals M. So suppose for the sake of contradiction we have M is not equal to 0, but AM equals M. Okay. For a finitely generated A module M. So the finitely generated condition is important. Okay, so we're going to choose a minimal list of generators. Let's say E1 through En for M. Okay, so what does this mean? This means that no smaller list of generators, or no smaller list of elements generate M, and this is always possible because I can find, well, yeah, so this is always possible. You could consider the, so this is always possible. For example, consider a set of N such that there exists M1 through Mn generators for M. This set is it's non-empty because M is finitely generated. It's a non-empty set of natural numbers, so it necessarily has a minimal element, and then that minimal element will give rise to a minimal set of generators. Okay. This non-empty set of natural numbers. has a minimal element. Which gives rise to the EI above. Okay. Okay, so I've got some minimal generators, and as you can guess, we're going to use this assumption to construct a smaller list of generators. Okay, so we can write E1. So since E1 is in mathfrak A times M, we can write E1 equals A1 E1 plus AN EN with EI, well, sorry, with the AIs in my ideal mathfrak A. Okay. Then we notice then 1 minus A1 E1. Right, if I subtract this guy over to the other side, this is A2 E2 plus AN EN. Okay, and the thing to notice here is consider this coefficient here. Note that 1 minus A1 cannot be in our maximal ideal, since A is a proper ideal, so A1 can't be a unit, so it has to be contained in this maximal ideal. Okay, remember, M contains everything that's not a unit. M splits our ring A into two sets, units and non-units. A1 is a non-unit, so it's in this thing M. 1 minus A1 is not an M. Okay, I didn't finish my sentence here. Since A1 is in M, and if 1 minus A1 were also in M, then 1 would be 1 minus A1 plus A1, which would have to be an M because it's an ideal closed under addition. Okay, however, M is a proper ideal. Okay, so 1 minus A1 is not an M. In particular, it must be a unit by our remark above. Okay, what does that tell me? This tells me that, well, I can multiply by 1 minus A1 inverse now and get that E1 is 1 minus A1 inverse A2 E2 plus 1 minus A1 inverse AN EN, so that actually I can actually generate the entire module by E2 through EN. Okay, this contradicts our assumption of minimality. Contradicts minimality of N. Okay, I screwed this up. Minimality of E1 through EN. Okay. So this proves step A. Okay, to prove step B now, you essentially just apply the result to the quotient. So to prove B, I'm not going to go into too much detail here. To prove B, consider n mod n and apply Nakayama, I guess maybe, and apply part A. Okay. So you'll see essentially that if n plus mathfrak a m equals m, then if you replace m here by the quotient m mod n, then you'll have this, so that the quotient has to be 0, and therefore n has to be m. Okay. So there's a small exercise to work out the details in part B. Okay, so these are the main results we need about local rings. We'll talk about how local rings appear and where these things come from in number theory in the next section. So, yeah, see you next time.